Hello everyone. Today I'm going to explain the basic structure of transformers and their design. Uh, of course, this is the second unit in your subject according to Anna University syllabus, Basic Electrical and Instrumentation Engineering. That is BE 8254. The unit 2 is about transformers. So I'm going to give a brief overview of the transformer structures, how it is designed, why it is designed like that. Okay, we'll see this. So where the transformers are used, if we understand the basic power systems, so where we have the transformers near to the power stations, where we step up the voltage that is generated from the power station. Generally, it will be 11 kV. Power station will be generating 11 kV, and we will step up transformer we will use here, and we step up that to approximately it is to 132 kV. Okay, so we have one type of transformer we have is step up transformer, and we step up that to 132 kV and transmit through the overhead transmission lines, and after reaching to the cities or towns, we step down that voltage back to 11 kV using another transformer called a step down transformer. So basically, a transformer is a device which will step up the voltage values from low value to high value or high value to low value, which will steps up or step down the voltage levels of input values. Okay, so after coming to the cities, these voltage levels are again converted back down to 132 by 11 kV, and from 11 kV we will have some other transformers where we again step down 111 kV to, that is either 230 volts phase voltage or 440 volts line to line voltage, 230 volts or 440 volts, which we use the power, that is the voltage levels which we use generally to our homes. So we have transformers in the power systems. One type of transformer is step up transformer, other type is step down transformer. And also even after coming to our houses, every electronic appliance what we use in our house, like your TV or your laptop, all these devices are electronic devices which operates normally on 5 volts or 12 volts range. Electronic devices operates on. So you are getting 230 volts to your home, so you may require one more small transformer to make your electronic devices to operate, like 230 volts by 12 volts or 24 volts or 5 volts, depending on the electronic device. So we classify these transformers into two types or three types, you can call it as. One is called as power transformers. Okay, power transformers are nothing but which are used in the power system, where which are very high values, 11 kV by the 132 kV or 132 by 11 kV, which is power range is very high, power transformers. And this 11 kV by 440 volts or this kind of transformers we have, we call it as distribution transformers. Okay, based on the voltage ranges we classify them distribution to the houses. Okay, that's why it's called as distribution transformers. And the small transformers which we have in electronic appliances like TVs and your laptops or any other device, we can call it as electronic transformers we have. Okay, electronics transformers. Okay, so how do they look physically? If you see, before going for the construction side, you might have seen the transformers somewhere on the roads. This is a power transformer which is of very big size, which can be like if it is a step down step up transformer, it will step up from 11 kV by 132 kV. This range of transformers, we call them as power transformers, which are used in substations. Substations are power stations, power generating plants. Or you can say this is step up transformer 11 kV to 132, or you can call it as 132 by 11 kV. We can call it as step down. So both ways we have to do step up and step down in the power transmission. So this is just to show you the picture of power transformer. Then we have distribution transformers, where we can see nearby our houses we have some small transformers compared to the previous one. This is called as distribution transformer. Like this can be like 11 kV to 11 kV by 440 volts line to line voltage, or it can be like this is line to line voltage LL, or it is 230 volts line to phase. V phase voltage can be 230 volts. So distribution transformers will be looking like this. The range of them will be like this. And what is electronic transformer? Of course, these things you can see when you open or stabilizers, various different electronic appliances. You can see this kind of small transformers inside. So transformer sizes varies depending on the place where you have, or the power rating that are used or designed for. Okay, it can be near the power stations, it can be near the houses, distribution transformers, or it can be inside the electronic devices like TVs or refrigerators or any other things. Okay, so what is there inside this device? All these devices works on the same principle of electromagnetic induction. So what is there in these devices is, this is the basic picture of any transformer. So inside a transformer we will have two windings. One is called as primary winding and another one is called as secondary winding. Okay, primary winding is the input winding. Let us say this is, if I give 11 kV here, primary winding is the input side, where if I give 11 kV here, for example, it's a distribution transformer, I will get at the output, I will get like 230 volts. 11 kV is 11,000 volts, is stepped down to 230 volts. How it is stepped down is, basically we'll have two windings inside the transformer. Primary winding, that is this winding we have here, this is called as primary winding, and this winding we have here, we can show like this. This winding we have here, this is the secondary winding. One primary winding and one secondary winding. Two windings will be there, which are wounded on a metal body, which is called as core of the transformers. Okay, so these two windings are placed on a, or wounded on a metal steel core body. Okay, why this steel core is used? We have some reason. So what is the principle of transformer operation is, it operates basically on electromagnetic induction principle. So when we give some voltage to the primary winding, some current passes, I current passes through this winding. When the current passes through this winding, there will be some magnetic flux generated surrounding this primary winding like this, both sides. Okay, you all know the basic physics. There will be flux generated surrounding this coil or winding. Okay, now this flux will extend up to this secondary winding also. Okay, it may extend, it may have bulge like this, it may extend to some distance. This flux will have expansion and compression when we give the AC voltage. Okay, when voltage goes up, positive cycle, the flux will expand, and when it comes down, the flux will compress. So now when we place a secondary winding, when we bring a secondary winding near to that flux, the vice versa, the dual of the thing will happen. That is, when you pass a current through a winding, electromagnetic flux will be generated, and when you bring another coil inside that electromagnetic field, a current will be induced in this new winding, secondary winding, which is brought into that magnetic field. So this is from the basic principles of physics, okay, Faraday's law and all those things. So the secondary winding will be getting some current because of this electromagnetic induction. Okay, when an secondary winding is brought into the effect of the primary magnetic flux, a current I2 will be induced in that, or electromotive force will be induced in that winding. The current starts flowing in that secondary winding, and when we take the potential difference between these two terminals, we will get some voltage there. And this number of turns ratio, primary coil will be, number of turns in the primary coil will be of different value compared to the number of turns in the secondary windings. So that ratio V1 by V2 is given as N1 by N2. That is means that, okay, that what is that means that this voltage ratio between primary and secondary will be related by some equation like this. V1 by V2 is equal to N1 by N2. So there is the derivation for this. Okay. For example, if you think like V1 is 11 kV and I want to get 230 volts at the secondary side, and let us assume that your primary you have fixed to some number of turns, like some 1000 number of turns, 1000 turns like this. If you have fixed for that, okay, 1000 turns, you can decide for this voltage ratio, you can decide what is the number of turns N2. And from this calculation, from this formula, we have to decide what is the number of turns required. And these two are, this voltage will be directly proportional to the number of turns. Okay. Now, physically, and one thing we have to see here, as I told you, to see in this picture, when the current passes, this flux will be generated all over the surrounding this primary coil. So generally the physics says that this flux will be densed at near to the winding. This is densed place. As you move forward to this thing, this flux density, you can say Bm, this flux density phi, or flux density will be thicker here, and it will be thin, that is less dense here. And if I bring a secondary winding like this into the effect of that magnetic flux, of course some current will be induced in the secondary winding, thus some I2 will be flown. Okay, but to make sure that this flux is not variable with time, I want this flux to be flown smoothly and with a fixed value, like with respect to time. So for that, what I will do is, I want to make this flux to pass to the secondary in a structured manner. Okay, that is why we cannot place these two windings in the air. So when I want to make this flux to flow in a structured manner, I should have a metal piece. I should have a metal piece placed between these two fluxes like this. Let's say if I place some core like this, core, this flux what is generated in the primary will now take this metal body, metal core, and passes through this to the secondary winding. So this metal body or core is a medium, it acts as a medium to take that flow of flux to the secondary winding. So that is why this metal core is utilized. Okay, so that is what the structure shown in the picture. So why the metal core is, it is a part, metal core will carry the flux to the secondary winding. It acts as a path for the flux to reach the secondary winding in a regular way, without with a equal density. Okay, you can see the picture here. It is in a structured manner. The flux is flowing now. These lines, what are shown here, this is the flux. Okay, fine. Flux is now passing to the secondary winding in a structured manner. So this is, so now as flux, we can say now flux is not a variable thing. It is made as a fixed constant kind of thing without varying with respect to time. Okay, d phi by dt is the alternating flux. Okay, in positive cycle it moves one side, and negative cycle it moves other side. And now the relation is only depends on the number of turns v1 and v2. As I told you, v1 by v2 is equal to n1 by n2. Just the ratio of number of turns between the primary and secondary, these voltage ratios will depend. So this is the basic structure of transformer. Okay, so physically how do they look is, this is the physical look of core type transformer. Of course, we have two things here, two types of transformers. One is called as core type transformer, where the primary winding, this is primary winding and this is secondary winding. These two windings are wounded on a metal iron core or steel core. Okay, iron body, iron or steel. Okay, so this iron core or body, iron or steel body, is used to pass the flux, carry the flux in a smooth manner, in a structured way. Okay, so here if you see the structure, there is some problem here. If suppose this flux comes out of this winding like this, some part of the flux is going through out to the air. It is not entirely passed through the iron steel core. So some flux will be leaked out into the air. We call it as leakage flux. Okay, leakage flux both sides, in the secondary and the primary also. You can see there is no metal body at this side. So this is some leakage will happen both at the primary and secondary. So to avoid this thing, we have another structure called as shell type structure. So where the shell type structure, both windings are made inside the transformers. Previous structure, if you see, the windings were at the left and right. But shell type transformer, we have a center metal limb here. On this itself, we have the primary winding, and on the same thing, we have the secondary winding. The advantage here is the flux, even if the flux gets generated here, both on secondary and primary, that flux will not go wasted into the air. That will be linked with the metal body. Even if it comes to here, it is not wasted out. So this metal body will receive that and makes the flux to pass through it. So leakage flux will be minimized in the shell type transformer. That is the reason we go for this kind of structure. Mostly nowadays transformers are shell type structures. Okay, it looks like this. Okay, both are inside, not at this place. We are not making on this side or this side. This is core type. What we are doing is we are making one more metal plate here, and we are making the winding, one winding primary on this and secondary on this. This is shell type structure. This is not used. Okay, so this is the shell type transformer. The basic use of this is to avoid the leakage fluxes. Okay, so that is the basic construction and principle of operation of transformers. So just to give you the basic idea. Hope you understood. So thank you very much for listening.